Okay, welcome back. What I want to look at is semiconductor diodes, but I want to look at that in a broader sense because the semiconductor that is used to make up diodes is also can be used to make up transistors. So, but I decided that I would use the semiconductor diodes because they tend to be, well, all semiconductors are quite versatile in the sense. But that's what I decided to go with anyway. Okay, conductors, semiconductors and insulators. The category in which we place a material depends upon its ability to allow electron flow. A material that allows a large electron flow is called a conductor. So obviously most of you would be familiar with a conductor, which would be copper being one of the best conductors. Okay. Now, an insulator is a material that does not permit a large electron flow. A material of conductivity intermediate between that of an insulator and a conductor is called a partial conductor. Okay? Now, examples are boron, silicon, germanium, arsenic, antimony, tellurium, and all electrolytes. The two most important partial conductors are germanium and silicon. Look at the tables in respect of the resistivity of different materials. Now again, remember, take your time to read the information, extract it, make it your own. Do some additional research so you can see, add to what has been given here. Okay? This is only a sample as to what can happen or that relates to certain materials in regards to certain types of semiconductors. Now, graphs of resistance to base of temperature for conductors, insulators, and semiconductors are shown in figure 7.1. For convenience, it is assumed that we can have three types of material, each at 0 degrees Celsius. And please note, purely for convenience, okay? From the graph, it can be seen that the resistance of the conductor rises with increase in temperature, but the resistance of the semiconductor decreases. So here, from the graph, it can be seen that the resistance of the conductor rises with increase in temperature. So the resistance in regards to a copper conductor that resistance will increase when the conductor begins to get hot. But the resistance of the semiconductor decreases. The insulator resistance tends to remain constant until it reaches its breakdown temperature and fails to act as an insulator. And you've seen this before in diagrams given to you in the workshop, and maybe even some experiments showing that the effect of overheating of cables in regards to its insulation. Yeah. So just to recap, the insulator resistance tends to remain constant until it reaches its breakdown temperature and fails to act as an insulator. An example of this would be an extension lead with a number of appliances connected to it. It could begin to overheat and the insulator would begin to melt. Now, if the temperature of germanium is raised above 100 degrees Celsius, the material is damaged, whereas silicon can stand up to about 200 degrees Celsius. In practice, Germanium devices are not used much above 65 degrees Celsius and silicons up to 150 degrees Celsius. So if you were designing something to operate in the Sahara Desert, you obviously need to be looking at something that can withstand a high temperature. So most of your product would then be in silicon. And here we have germanium crystals. This is just a germanium crystal, pure germanium as a crystal block. Okay, that's all I've done here to show you. And here what happens then, these are taken off as wafers, so it goes through a machine and it's just skimmed like a wafer, like you're skimming a biscuit. Okay, and these wafers are quite thin. Okay, now a germanium crystal GE has 32 protons, 41 neutrons and 32 electrons. The nucleus containing the 32 protons and 41 neutrons, and the inner electron shells containing 28 electrons. Now, feel free to expand this further for your own edification or for your own knowledge gaining. And look at these yourself. You'll find that there's quite a number of books that shows you how it is formulated. But here I'm just giving you information as a purely information basis on the background of the semiconductors which is in use. And please note there's quite a few, so this is by no means exhaustive. The remaining 4 electrons are called valence electrons. Now the remaining 4 electrons are called valence electrons. Now look this up for yourselves, okay? Because it links back to what we were talking about here in regards to this here, okay? But because I simply step ahead, I'm making an assumption that you would have some prior knowledge of this, but which is not always the case, so please do forgive me for that. But do some groundwork for yourself to find out what valence electrons are, okay? When 2 or more atoms are close together, we have so-called valency bonds, valency bonding, okay? And that was shown in figure 7.3. In pure germanium crystals, electrons have little freedom of movement, and the material has a high resistivity. It is known as an intrinsic semiconductor, okay? But when we dope the semiconductors, elements such as antimony, Sb, arsenic, and phosphorus have 5 valence electrons. So we're now doping the germanium with one of these materials. These elements can be introduced in small quantities to germanium and other intrinsic semiconductor materials to give N-type semiconductor materials, okay? So what you end up have is, you've heard of your NPN transistor or your PNP transistor, etc. Here it is just the materials which makes up that change, which has been doped to create these various types of semiconductor materials for us to use. Now again, do some reading for yourself, do some ground research, look at the intrinsic N-type materials and so forth. A crystal with 1 atom of antimony is shown in figure 7.4. The adding of controlled amounts of impurity is known as doping. In this case, it produces N-type semiconductor material. This contains numbers of free electrons which carry a negative charge. Elements like aluminium, gallium, and indium In have the free valence electrons. When indium is used as an impurity in germanium, it accepts rather than donates electrons to the crystal. Since this acceptor has only free valence valence electrons, one of the neighboring germanium atoms has a vacancy in its outer shell. Excuse me. Now, any electron which moves so as to fill this vacancy will have vacated its own shell, leaving a positive charge. These positive charges within a semiconductor are termed holes. We now have a p-type semiconductor material as in figure 7.5. Now, properties of holes. A hole is a position which has been vacated by a valence electron. And please note that when we talk about holes here, we're talking about the electronics and the doping of materials in regards to the electron state and the atomic vacancies, okay, which has been vacated by a valence electron. It is convenient to consider a hole as an actual particle carrying a positive charge. An electron situated between two oppositely charged bodies tends to move towards the positively charged body because like charges repel and unlike charges attract. Now, a hole will move towards the more negative of two charged bodies. In normal metallic conductors, the current is carried by free electrons, which move from the negative towards the positive terminal of a cell, as shown in diagram 7.6. This is also true of N-type semiconductor materials. However, in a p-type material, it is the holes rather than the electrons which are free. They are attracted to the negative terminal of the cell as in figure 7.7. There are large numbers of free electrons in the negative terminal of the cell, so that when a hole reaches this point, an electron from the cell enters the material and fills the hole. Now, at the same time, the positive terminal of the cell exerts a force on the electrons in the electron pair bonds of nearby germanium atoms. An electron pair bond breaks and one of the electrons freed goes into the positive terminal of the cell. The breaking of this bond and the loss of an electron to the terminal creates a new hole. This action is repeated and repeated again and again. Now, these materials which goes to make up a transistor allows us to control two currents which are available at the transistor. One current would be the base current, the other would be the collector current. And if you look at the video I did in regards to the monostable multivibrator circuit, you'll see that I've indicated two transistors there, indicating the base, emitter and collector. And you'll find that this is how those transistors are constructed and made up. And here we have symbol abbreviations, okay? And most of you will be familiar with the current I, resistance R, resistivity, rho, temperature, okay? Unit, ampere, ohms, Kelvin, okay? And here, now the temperature difference is commonly expressed in degrees Celsius instead of kelvins. It is useful that the unit of Celsius and Kelvin scale is the same. 1 degree Celsius equals 1 degree Kelvin. A temperature expressed in degrees Celsius is equal to the temperature expressed in kelvins, less 273 degrees. Okay, so here, now that should, I would have said that this would, because this here is simply 400 degrees, could be 400 degrees Celsius, but here we simply put it as 400 Kelvin. But I would have simply put this as 400 Celsius. So 400 Celsius minus 273 Kelvin will leave me 127 degrees Celsius. And let me just make sure I've got that right, because I didn't confirm it. Yes. Okay. Okay, so here, again, that will give us 400 degrees, 127 degrees Celsius. But remember that 1 degree Celsius is equal to 1 degree Kelvin minus 273 degrees. So if I assume a figure of 100 degrees Celsius minus 273, it will then obviously be it then obviously be minus 173 Celsius. Okay. Okay, let me just go a little bit, make sure that we get. Now again, write this out for yourself. Make yourself aware of the symbols and do this calculation here for yourself. Look it up, do some additional research. Make sure the information here that's given is correct, that you understand it as well. And here we have given you a list of materials and their relative resistivity in regards to their materials. Now remember that it says ohms per meter times 10 to the n. N could be any figure, okay? And here we have insulating material, asbestos. But again, please remember that asbestos is no longer used as an insulating material such, as we know the hazards of asbestos. So please, again, remove this from sight, basically. But be aware that you may still come across it in certain old type buildings. And yes, and you can say, well, polyvinyl chloride, PVC, and I believe it is relating to PVC, equals 10 to the 14. Okay. And here you have semiconductor material, germanium 0.1 to 60 ohms per meter, and silicon with a lower resistance. Now all this graph does a graph of resistance to a base of temperature for conductors, insulators and semiconductors. And as you can see that conductor in regards to as the, let me see if I got this up right. Okay, let me just make sure I get this in. Okay. Yep. Here we have our conductor resistance, and all we're saying here is that the resistance in regards to the conductor rises in regards to temperature. So here the conductor rises, the insulator remains the same at a given temperature until it reaches the point of breakdown. But for the semiconductor, the temperature, as the temperature increases, its resistance seems to decrease. So you can see that a semiconductor has quite valued properties. And again here, figure 7.1. Now here's where we were talking about the holes and so forth and valence electron. Do some research for this for yourselves, because you need to understand or have some prior knowledge of as to what I'm talking about in regards to germanium and valence electrons. Okay. A similar thing in electron pairings. Okay, here electron pairing in regards to germanium. Okay. And if you look back at the text, when you read it, you can look back at it. I'm not going to look back at it. I will leave that to you. But you can see that here we are showing the excess electron, which becomes movable. Excuse me. And here we're moving now to fill our holes. So here's where we have our holes, and we then need to move to fill our holes from one place to another. Okay. And here we have electron flow. Now this is not conventional flow, this is electron flow, okay? So please bear that in mind. Negative to positive. And you can see now here, what all we're showing you here is that we have what we call hole flow. So we have hole flow flowing from positive to negative, okay? But these are just movement of electrons themselves within the components and the germanium crystals which we're dealing with, okay? That's what enables us to have a NPN and PNP transistor type, depending on which direction you may wish to have a hole flow. And again, please answer the questions. Okay, all the answers is in the text. Okay, there's nothing there that you have been asked that has not been written into the text. But do some additional research for yourselves. I'm just making sure that we have got all the information in and everything is within shot. Okay. Okay, just checking and making sure that all bits there. Now read the information, write it out for yourself if need be, do some additional research for yourselves, do the groundwork, okay? And you'll find that it all comes together. Now bear in mind that this is done with the view that some people may have prior knowledge of some of this, so it will be more understandable to those. If you haven't, then do some reading for yourselves. Okay, thank you. That will be it for today. I hope you found this useful. Bye bye.